Legends are few and far between, but when you meet one, it blows your mind, and they make a real difference to the whole of society.
Tonight, we're in Oxford to tell the story of an extraordinary physicist who faced challenge after challenge, yet made a famous discovery that changed the face of astronomy forever.
She has been a maverick in the field, and in fact, her discovery actually started a new subfield in astronomy.
Without Jocelyn, I wouldn't be here.
Welcome to the sky at night. When I arrived in Cambridge, I felt like a country yokel. And I thought, they've made a mistake admitting me. I'm not bright enough for this place. They're going to discover their mistake, they're going to throw me out. But until they throw me out, I will work my very hardest so that when they throw me out, I won't have a guilty conscience.
Professor Jocelyn Bell Burnell. She's a discoverer, an explorer of the distant cosmos, and she's walked amongst the stars. But in 1965, she was just a student, about to start her PhD.
Radio astronomy was still fairly new at that stage, so there was a lot going on, a lot of interesting stuff happening. It was an exciting time to be involved.
Jocelyn's supervisor, Professor Anthony Hewish, had grand designs for a new state-of-the-art radio telescope.
I didn't initially realise how big a telescope Tony was planning. At the point I arrived, he had the money to build the telescope. I think he had at least rough designs, but there was, so to speak, nothing on the ground. And when it became clear it's 57 tennis courts in area, it's huge. It took 2 years to build. There were about half a dozen of us working on it. I was doing quite a lot of sledgehammering, became quite strong, and then we switched it on. Radio telescopes often don't work first time, but this one did. It worked.
With 120 miles of wiring, the world's newest radio telescope was complete.
So I was straight into observing. And then I had miles and miles and miles of chart paper pouring out of chart recorders, which I would take back to my desk in Cambridge and sit and analyse.
We all use radio waves every day. And just as you can tune your car radio to hear your favourite music,
What else is on the radio?
by tuning a telescope to the skies, you can listen to the universe's greatest hits too, if you can tune out the static. The signals arriving at Jocelyn's telescope were buried in a cacophony of interference. But with her sharp memory and keen eye, she spotted something that no one had before.
It was when I saw this little bit of scruff and said, oh yeah, I've seen this somewhere before, haven't I? My data comes out on long rolls of paper chart, and I have the previous rolls stored in boxes. So I get out the box that covers this bit of sky. I was fortunate in that the grad students worked in an attic, and there was a great big long space down the middle of the attic between our desks. So I took over this space and spread out my charts for the observations I'd already made of that particular strip of sky.
Jocelyn had identified a signal measuring just a quarter inch in hundreds of feet of data. Her diligence was about to pay off.
We needed an enlargement. And with paper chart, rolls of paper chart, the way you get an enlargement is to run the paper faster under the pen and everything gets spread out. Very neat. And right from the start, as I ran the paper faster under the pen, I could see going blip, 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 always the same beat, but 1 1/3 seconds apart, which is totally unknown in astronomy. What the heck is this?
For an astronomer, the rate of a pulsing signal indicates the size of the object. For something astronomical to produce pulses every 1 1/3 seconds, it must be spinning once every 1 1/3 seconds. The thought was preposterous. No object had ever been observed that could be as powerful yet small.
I took the trouble of phoning my supervisor and said, "Tony, it's a string of pulses 1 1/3 seconds apart." "Oh, well, that settles it. It's man-made." And put the phone down.
Artificial or not, what was causing this strange signal?
So one of the problems was, is this some foible of my telescope? Have I got some wires crossed? Tony and I spoke to another academic and his grad student to see if they could help us. They had a separate radio telescope, separate receiver, on the same site, but working on the same frequency, the same channel. One day, 4 of us went out to the observatory. Robin and his supervisor, me and Tony, my supervisor. And the way the telescopes were aligned, my telescope would see it first, and Robin would see it 20 minutes later or something like that. My telescope observed it, the thing was pulsing nice and strong, it was good and healthy. And then we went and stood by Robin's equipment, and nothing happened. And Tony and Paul, the 2 academics, started walking down this long laboratory. I was padding along behind them, and they were saying, "Now, what could it be that shows in this radio telescope but not that one? Could it be da-da-da-da-da? No, it can't be that because, oh, could it be ba-ba-ba-ba-ba?" Robin has stayed by his pen recorder. We've got down this long laboratory, and suddenly there's a shriek from way back there, "Here it is!" And we went charging back, and there were the pulses coming in, seen by a separate radio telescope with its own receiver and its own chart recorder. Robin had miscalculated by 15 minutes when his telescope would see that bit of sky. If he'd miscalculated by 1 hour and 15 minutes, we'd have all gone home, and the story would be different.
Jocelyn had discovered a pulsar, a zombie, the leftover core of a cataclysmic explosion at the end of a star's life. One of the most extreme objects in the universe.
When a star dies, it sheds its outer layers, but what remains collapses. Like an ice skater going into a spin, when an object shrinks, it spins faster. The more dramatic the collapse, the faster the resulting spin. And it's this spin that means that pulsars pulse, that we see regular bursts of radio waves. Like Earth, pulsars have magnetic fields. Particles are channeled along the magnetic field lines, and in the exotic environment around a pulsar, they produce jets of radio waves aligned with each magnetic pole. Now, the magnetic pole won't be aligned typically with the rotation axis of the pulsar, and what that means is that we get something like this. From Earth, we see flashes of radio waves as each beam sweeps across us. A cosmic beacon, a lighthouse shining out into the darkness.
Jocelyn had opened up a whole new area of study. Pulsars are laboratories for extreme physics. So extreme that scientists are still investigating their secrets to this day. I've come to Royal Holloway, University of London, to meet Dr. Vanessa Graeber, to find out what we know about their guts.
Astronomers usually like to give names to certain subclasses of things. So neutron stars is the compact object that we have outside in space. And pulsars are those specific neutron stars that actually produce this lighthouse type of radiation.
An incredibly high density.
Yes, so it's really like an object that's the size of a city like London, but weighs something between 1 to 2 times as much as our sun. And if you think about sort of like the quantities involved, if you compress the sun or twice the sun into the size of a city, you end up with really extreme densities. That is something that we really can't produce on Earth.
Seeing something in space the size of London is challenging.
Very, very, exactly.
I suppose that's why your work is so important, because we're modelling this, because we can't really get up close and personal to see it.
So to a first instant, we can either say, okay, look, this is like a massive fluid ball, and then we can write down a set of equations, and then we build it up from there.
Yes.
So you have to come up with some additional ideas on how you can make this model more realistic. And in the case of the neutron star, what's generally happening is that we don't just have a fluid ball, but this fluid interior is surrounded by a solid crust.
Pulses of radiation that are emitted from the star will usually slow down over time. Sudden changes in this pattern can give away crucial clues about the star's interior. Now, this periodic signal, I was told that it's one of the sort of most reliable things in the universe. That's all,
Yes, yeah.
Great precision, but not always.
Yes, that's true. Which is like the thing that my heart beats for. Yes.
This is your research.
Yeah, this is like what I work on a daily basis, which is the fact that some of the neutron stars, while they spin down, and this was actually observed very early on after the first neutron star was discovered, is that some neutron stars show what I like to call hiccups. So they don't just spin down, but there is this occasional interruption where the star suddenly rotates a little bit faster.
By studying the pattern of the hiccup, the change in spin, we can get an insight into what's happening inside the heart of the star. To explain, we'll need the help of a couple of eggs.
Okay, so we have 2 different eggs, and we're going to try and do a little experiment that you can also try at home. So we'll start with this one. And what I'm going to do is I'm going to rotate the egg, and then I'm going to use my finger to quickly stop the shell, and then we're going to look at what's actually happening. Okay, so this is the egg. I'll stop it. Try that again.
Rotating.
Exactly.
Put this one out.
Okay, let's try this with this one. Okay, we try the same thing. I'll stop the egg with the finger, and what we see is it does rotate a little bit more afterwards.
It does.
Okay, we do exactly the same thing for both eggs, and we do see something very different happening.
Yes, yes.
So, should we reveal what's happening?
I can guess.
Yes, yeah. What do you think? What do you think is the difference?
And so I think one is more fluid than the other.
Yes, the interior.
And this one, I guess, is the raw egg.
Yes.
And this is hard-boiled?
That's correct.
Okay.
So in the case of the hard-boiled egg, basically the individual components, so the shell, the egg white, and the egg yolk, are all just connected as a single component. So initially, when you spin it up, everything rotates at the same speed. But in the case of the raw egg, if I rotate things, it will take a little while for the interior to actually start to rotate, and then once it is rotating, I just stop the shell. I only stop the shell, but the interior actually continues to rotate.
Lovely.
And I basically see the exchange of angular momentum, very similar to what's happening in the neutron star, between the internal component that rotates faster and the shell that I've stopped.
In the case of the neutron star, instead of egg white and yolk inside, it has exotic forms of matter that can flow without friction. A superfluid.
We started talking about a neutron star being modeled as like a fluid ball, but the interactions of the superfluid itself are really not driven by this like London-sized object, but actually by like tiny quantum effects. So the superfluid has a special property that it rotates in a very different way by forming these tiny quantum tornadoes.
So we're looking at the macro,
Exactly.
the micro, and the nano. Since the first observation of a pulsar, over 4,000 more have been detected. But Jocelyn was on a path that would swiftly take her away from Cambridge and away from her pulsars too.
I got engaged to be married between discovering pulsars 2 and 3, and was fool enough to wear the engagement ring into the office. I was very proud of it. And that sent a message that I was leaving. Because in those days, married women didn't work. It implied that your husband couldn't earn enough if married women worked. You were going to be a housewife, a wife, and probably a mother in due course. This wasn't actually my plan, but I see with hindsight that that's the message I was sending out.
Once married, Jocelyn's work was entirely dependent on her husband's postings.
Husband would say, it's time I moved to get promotion. There's a job going in X. Is there anything astronomical anywhere near there that you might get a job? So I've had a very disrupted career. It's been great fun, great interest, but a lot of it's been dictated by where my husband was working.
Since Jocelyn's discovery, the radio sky has continued to surprise. Dr. Kaustubh Rajwade at the University of Oxford studies the oddballs of the radio family and what these outsiders can tell us about the cosmos. Hey, how are you?
Hey, Chris. Nice to see you.
Yeah, you too. Now look, you like to look for weird things in the radio sky. What have you found?
Over the past few decades, we have found all sorts of unusual neutron stars. Back in 2007, people at that point were looking for pulsars in data taken by all these radio telescopes around the world.
And often looking in archival data as well.
Yeah, absolutely. In West Virginia University, Duncan Lorimer, who's a professor there, and his undergraduate student, Dave Narkevic, they were searching through some of this data taken by the Murayang radio telescope in Australia, looking for pulsars in the Small Magellanic Cloud.
Okay, our neighboring galaxy.
Yeah, and so while going through the data, Dave actually found this very interesting single radio burst. And
Not a repeat, not like a pulsar where you get all these pulses, just one.
Just one. And interestingly, they realized that this burst could not have come from our galaxy, and also not from the SMC, but way beyond that. And the reason that they could figure this out was because of something called as dispersion of radio waves. So, as you know, there's a lot of stuff between pulsars in our galaxy and us, right? There are these electrons and plasma that's floating around. And so this plasma actually acts like a prism. And so, which means that the radio waves that are at lower frequencies are reaching us much later than the radio waves at higher frequencies.
Oh, just like, because a prism would bend blue light differently from red light because of the difference in wavelength. Which is the same as difference in frequency.
Exactly.
Yeah, okay.
We now know these objects as FRBs, or fast radio bursts. A blast of radiation that for a few milliseconds can outshine an entire galaxy.
What do they tell us about the universe and the galaxy through which their light travels?
Yeah, I'm glad you asked that, because we can use them as independent probes of cosmology. And one of the key aspects in which FRBs can help is this so-called missing baryons problem.
Baryons, is this just normal matter? Electrons, protons, oxygen, hydrogen, helium, all the rest of it? Yeah.
Some of it we can see. Light is our only source of actually detecting and seeing these baryons in the universe, but a lot of it is so diffuse that we just cannot see it at any wavelength, like they're not emitting any radiation. But because FRBs are so fast and only last for a millisecond, which means that you can see dispersion in them. And then you know that the total delay that you see in your radio band because of the dispersion has contributions from your galaxy, has contributions from the host galaxy, but you also has contribution from the diffuse baryons in the cosmic web.
It's really rather lovely that the light from something like an FRB tells us about everything it's passed through.
Exactly, and you're literally weighing up the universe.
Yeah.
So if you have enough FRBs that are well localized with well-known distances, all across the sky, you could map out the cosmic web. And that's just, I think that thought really gives me shivers.
With the work of physicists like Vanessa and Kaustub, Jocelyn's legacy is strong today. But in the wake of her discovery, she endured shocking discrimination.
So journalists would interview Tony and I together ultimately, and they'd ask Tony about the scientific significance of this experience. And then they'd turn to me for the sexual content. How many boyfriends did I have? What were my bust, waist and hip measurements? Really important questions like that. And the photographer similarly, could I undo some shirt buttons, please? It was thoroughly degrading. Young women were sex objects, full stop. Never mind if you'd made a major scientific discovery, you're a sex object. Tony did nothing. Absolutely nothing to stop it.
Jocelyn's treatment would extend to the most prestigious accolade in all of academia.
It was 1974, and I remember the day very well. I was working in X-ray astronomy by then. This particular day, our satellite has launched 8 o'clock in the morning. And about 2 minutes past midday, a colleague comes bursting into my office. Have you heard the news? Have you heard the news? I thought, oh my God. The satellite's gone in the drink. But it wasn't. It was the announcement of the Nobel Prize award to Tony Hewish and Martin Ryle, my former supervisor and the head of the group.
Well, in essence, it's...
Cambridge's Martin Ryle and Tony Hewish had won the Nobel Prize for their pioneering research in radio astrophysics. Ryle for his observations and inventions, and Hewish for his decisive role in the discovery of pulsars. while Jocelyn, despite being integral to that work, missed out on the acclaim.
At the time of the Nobel Prize, women still weren't regarded as serious in the male world. It's really only in more recent years that women are recognized in their own right for their own abilities. Thank goodness. If you have a group of people that all think the same, it's great fun for them, and they do good work, but they fail to see anything out in the wings. Whereas if you have a diverse group, you're more likely to pick up on the new threads.
Jocelyn has since won numerous awards for her work, donating prize money to fund the Bell Burnell Scholarship. PhD student Ida Say from the Mullard Space Science Laboratory is a current recipient.
Hello, Ida.
Hi,
Great
so
to meet
nice
you.
To meet you. Same.
I gather you're at MSSL.
Yes, I am. Yeah.
Yeah, wonderful place. I worked there for a
thank you.
while.
Yeah, I've heard we were on the same office.
Really?
On the first floor.
That's
yeah.
right.
Yeah.
I had the desk in the window looking out over the front door.
Yeah.
You see all the comings and goings.
Yeah.
So, exactly what are you working on, Ida? What's your thesis going to be about?
So just trying to make the most out of the data from the Gaia satellite,
Right.
which was launched a few years back and
Yes.
has been quite remarkable with
Yeah,
galactic
yeah.
astronomy. So just
Yeah.
trying to use that data to understand the structure of the Milky Way, understanding where the spiral arms are, the different populations, and
Yeah.
the bulge and kinematics, and just trying to understand the history of our galaxy.
It's quite complicated to do that because we live inside it.
Yeah.
If it was
yeah.
another galaxy that you could look at, it'd be a lot simpler.
It would be simpler, yeah.
So have you always wanted to do astrophysics, or has it been quite a journey for you?
It has been a journey. I feel almost like a serendipity thing. I liked maths in primary school and secondary school.
Good.
I liked solving equations and doing algebra, and astrophysics just sounded cool to me, and I just wanted to try it.
Yeah.
And I tried it, and I fell in love, and here we are.
Yeah, that's fantastic.
Well, thanks to the scholarship. So, what prompted you to do that?
Well, I was awarded $3 million by the Breakthrough Foundation, and had to think rather rapidly what to do with that money, because if it's announced you've got that kind of thing, the phone keeps ringing.
Can imagine.
So that's when I decided to give the money to the Institute of Physics to set up these scholarships. You've got one, congratulations, to enable people from minority groups, minority in physics groups, which includes all women, to do PhDs.
Yeah, it has helped me, so.
Good. I did my PhD in Cambridge. I'd never been that far south before, and it was really scary. There's all these young men walking in the streets talking in terribly loud voices about what Hegel said and what Hegel didn't say. I thought, oh my God, they've made a mistake admitting me. And there were very few women in Cambridge at that time as well. I really suffered what's known as imposter syndrome. I don't know. Has that ever affected you, because you're also a minority person in another way?
I also went to University of Cambridge for,
Right.
and definitely the imposter syndrome was, it was off the charts. Because there's not many women doing physics, there's also not many people of color doing physics. I feel like I'm representing every person of color or every woman, that I have to do it so well, because if I don't do well, then it's gonna reflect badly on them.
Yes.
So it doesn't feel nice. But at the same time, it's a great source of motivation to try and be as good as possible.
I always felt that if I did something stupid, they'd say, trust a woman, no more women.
Yeah.
I guess any minority is under pressure. Yeah. Pressure not to let the side down. The more of us there are, the easier it gets. So please hang in there. Don't give up.
Yeah, I won't. Yeah.
Good.
If you're feeling inspired to do some of your own astronomical exploring this month, then Pete has got you covered.
Over the coming months, there are 3 phenomena which give us a perfect opportunity to do a refresher on terminology which astronomers may meet quite often: occultations, conjunctions, and eclipses. A conjunction is a term which describes when two or more objects, which are normally vast distances apart, appear in the same area of sky together. Or if you want to get technical, it's when those objects share the same set of celestial coordinates. To see Venus and Jupiter at conjunction, look towards the northeast horizon around 02:40 AM on the morning of the 12th of August. While the two planets are really located hundreds of millions of miles apart, their positioning makes them appear close together, about 2 full moons' widths from each other in the night sky. You can spot them again at the same time on subsequent mornings, with the gap between them increasing. Next we have occultations, and these occur when one object moves in front of another, hiding all or part of the more distant object from view. The upcoming occultation of Venus will take place during the day on Friday the 19th of September. You can find Venus low above the eastern horizon with the moon in brightening dawn twilight around 06:30. The occultation will take place between 12:45 and 14:10, so early afternoon. Please take care and use the correct protection when viewing through binoculars or a telescope, as you can cause permanent damage to your eyes if you look at the sun through a lens. Finally, in our trio of terminology, we have eclipses. The term eclipse means to obscure, so like occultations, it's one object hiding another. But typically with eclipses, we talk about one body casting its shadow onto another. A UK lunar eclipse is coming up on the 7th of September, but it will be a tricky one to spot. As the moon rises above the eastern horizon around 8 PM, it will be coming out of its total eclipse, so look out for a dark moon as it starts to appear. Once it has reached a few degrees above the horizon, you'll see it forming an odd shape as it exits totality. The main part of the eclipse ends around 9 PM. As the summer comes to an end and the longer and darker nights come in, there are plenty more events involving the planets and stars to look out for. And you can find out more in our detailed star guides available on our website at www.bbc.co.uk/Sky at Night. You can also find out details of our Flickr account there. And if you take any photographs, you can upload them, and you never know, they might appear on the programme. Here are some of our recent favourites.
One of the things I have learnt is if you don't get a Nobel Prize, you get every other prize that moves. Whereas if you do get a Nobel Prize, nobody feels they can match it. So you don't get anything else. So I've had parties almost every year for different prizes. Fantastic.
It's amazing to think that what started as nothing more than a blip on chart paper became the constellation of exotic objects that astronomers study today, all thanks to the fabulous, indefatigable, marvellous Professor Jocelyn Bell Burnell. Before we go, we're excited to announce that we're joining forces with the hit Radio 4 series Curious Cases, in a special programme solving space mysteries sent in by you.
Submit your space mystery questions to curiouscases@bbc.co.uk.
Good night.